Hi there, and welcome to your lesson on Coulomb's law. We pick up where we left off last lesson, kind of describing the characteristics of charge, what exactly charge is, and the characteristics of matter and particles that have charge and how they interact with each other. And today we take a look at Mr. Coulomb's research back in the day in the 1700s, as he attempted to apply to this electricity force what Newton did for universal gravitation, and that is to describe the interaction between particles in a mathematical format, taking off after Newton's tradition in describing nature in terms of math. So Coulomb was an engineer, an army engineer, and he was French, and he was in charge of designing and building different military apparatuses, and then when he was not in service, continued his inventions. And one of the inventions that he came up with was this torsion balance that we can see up here. And we'll take a look at that and how that led him to mathematically describe the force that is experienced between charged objects. So this lesson kind of picks up where grade 9 left off. And the first thing is for us to recall is that charged objects attract. That is, they pull towards each other, or an object is pulled towards another object if they're both charged, or they repel. That is, an object can feel a push away from another object that is also charged. And you remember, of course, and this is really important as we talk about Coulomb's law a little bit later on when doing the math, is that charges that have the same charge, in this case we'll call them positive charges, will push each other away. And that means that the orange charge is going to apply a force to the other charge, and at the same time, largely because of Newton's third law, the light green charge is going to apply a force to the other one. So both charges experience a force from the other force. And likewise, of course, wake up, pen. Hi there, and welcome to your lesson on Coulomb's law. We pick up where we left off last lesson, kind of describing the characteristics of charge, what exactly charge is, and the characteristics of matter and particles that have charge and how they interact with each other. And today we take a look at Mr. Coulomb's research back in the day in the 1700s, as he attempted to apply to this electricity force what Newton did for universal gravitation, and that is to describe the interaction between particles in a mathematical format, taking off after Newton's tradition in describing nature in terms of math. So Coulomb was an engineer, an army engineer, and he was French, and he was in charge of designing and building different military apparatuses, and then when he was not in service, continued his inventions. And one of the inventions that he came up with was this torsion balance that we can see up here. And we'll take a look at that and how that led him to mathematically describe the force that is experienced between charged objects. So this lesson kind of picks up where grade 9 left off. And the first thing is for us to recall is that charged objects attract. That is, they pull towards each other, or an object is pulled towards another object if they're both charged, or they repel. That is, an object can feel a push away from another object that is also charged. And you remember, of course, and this is really important as we talk about Coulomb's law a little bit later on when doing the math, is that charges that have the same charge, in this case we'll call them positive charges, will push each other away. And that means that the orange charge is going to apply a force to the other charge, and at the same time, largely because of Newton's third law, the light green charge is going to apply a force to the other one. So both charges experience a force from the other force. And likewise, of course, wake up, pen. Charges that are dissimilar experience a force. The force is an attractive force this time, so the negative charge feels a pull and from the positive charge, and the positive charge feels a pull from the negatives. So we can describe the force that each of these charges experiences as the electric force. And this is what Coulomb played around with transferring charges to pith balls. You can see there's a pith ball here that he transfers a charge as he dips his hand into this torsion, and he gives the same charge to the pink ball as to the orange ball there. And because they have the same charge, they repel. And you can see that as the movable pith ball feels the push away from the formerly pink ball, we can measure the angle of deflection. And that angle of deflection can be easily translated into the amount of force it takes to manually twist this torsion balance in the same way. So what Coulomb came up with was a relationship between the amount of force of repulsion that the movable pith ball experiences, and also he found that really depended on the inverse square of the distance between them. And this was pretty important because, as Newton discovered with his universal law of gravitation, the force acting between masses is also proportional to the inverse square of the distance between them. And so this is really quite important. The other thing that Coulomb found was the greater the charge that he imparted to each ball, the greater the force that was exerted between them. And so Coulomb came up with the following set of relationships, and that is the electric force acting on an object is directly proportional to the charge of one of the objects and multiplied by the charge of the second object and the inverse square of the distance between them. Now there was a piece missing, of course, as there usually is, and if you recall the universal law of gravitation, there's a constant, and there is a constant as well for Coulomb's law. Let's define these terms for you here. Fe is the electric force. K is called Coulomb's constant. I guess when you discover your own constant, you can name it after yourself. And we'll take a look at what that number is in a moment. Q1 and Q2 is the charge in coulombs. And then, of course, R is the distance of separation. Distance between the Q's. And that, of course, needs to be measured in meters. Coulomb also discovered not only the coulomb, the unit of charge, but also the relationship between some known principles, and that is 1 coulomb per second one charge flowing past a point, 1 coulomb of charge flowing past a position every second is what 1 amp is. And if we have a certain amount of energy, that is 1 joule of energy per coulomb of charge, that is equal to 1 volt. Now we'll come back to these guys. It's important to set it up now. We're not going to talk about them more today. It's important for your notes. We will return to these as we discuss other things. Let's take a look at this Q, because it's kind of interesting. We know the big G of gravitation is an extremely tiny number, 6.67 times 10 to the negative 11, tiny. And we know that if we were to drop a ball and let the force of gravity act on that ball, it will take, if we drop it 5 meters, it will take roughly 1 second to travel that distance. But once that ball hits the ground, once that ball interacts with the surface, it immediately accelerates at a far greater rate. Its impulse is severe, that is, its change of momentum is very high and very fast. As we consider what that interaction is, the ground and the ball falling on it, and we look really closely, it's easy for us to say that it's just hitting that other object. But what we know about the atomic structure is that atoms are mostly empty space. That's my attempt to draw an atom. We have the proton in the middle, electrons buzzing around, but most of an atom is empty space. And so when the ball strikes the ground, what makes it stop? What is applying the force against the ball continuing to travel in a straight line? What we come to know is that the protons in the matter of the ball are interacting with the protons, the positive charges, down here on the Earth. And it is a force of repulsion that is an electromagnetic force that prevents the ball from continuing to travel in a straight line at constant speed. So that electromagnetic force is responsible for arresting the motion of the ball extremely quickly. It takes 1 second for a ball to travel 5 meters with the force due to gravity on it, and it takes just a microsecond for the electric force to arrest the motion of the ball. So the K value of Coulomb's constant must be exceedingly large compared to big G. And we find that it is absolutely exceedingly large. The K value, Coulomb's constant, is an enormous number. And that number is 9.0 times 10 to the 9. Massive. There are some units as well that are associated with it. I'll omit those here. The units only serve to make the equation balanced by unit wise here. So Coulomb's constant, this is on your formula sheet. It's little k. Don't confuse it with the spring constant k as well. Most physicists use k for both of them, but they know when to use them appropriately. Okay, so that's Coulomb's law. And applying it to a problem is pretty straightforward. Let's take a look at an example where you might want to use Coulomb's law. And we'll draw some similarities next lesson between the force due to gravity and Coulomb's law. Okay, so let's say we have a charge A, and it is separated from a charge B. And B is a negative charge, and A is a positive charge, and they're separated by 20 centimeters. And we need to calculate the force that A experiences. Well, we can just line up our formula, Fe equals K Q1 times Q2 divided by R2. You can see that this is just kind of plug and chug. We got 9.0 times 10 to the 9 times Q1, which I forgot to give you. So the charge on A is 4.0 times 10 to the negative 16 coulombs. And charge on B, QB, is 2.5 times 10 to the negative 7 coulombs. So we can just plug in our numbers and see what happens. 4.0 times 10 to the negative 6 coulombs times 2.5 times 10 to the negative 7 coulombs divided by the R squared, which is 0.00 squared. So calculating the force felt on A will give us the magnitude. Now, how do we deal with the positive and negatives of the charge? More accurately, Coulomb's law should be written with absolute value signs assigned to each of these variables. We only include the negative sign when we're dealing with vector forces as we designate direction. So A is going to be attracted to B, and so Fe will turn out to be a positive number. And we assign that positive number only once we have identified which direction the force is going to be acting on A. How do we know? Well, we have to look at the charges themselves. If we have a positive charge and a negative charge, we know the direction is going to be that way. Okay, the force, the electric force, should never come out to be a negative number when using the formula. That means that you have done something wrong. The charges are the absolute value of the charges, not indicative, or not using negatives to indicate the type of charge. That's something to remember as we move forward. And you just have to kind of use your physics sense when analyzing what's going on. Okay, things get a little more interesting when we have a three-body situation, and we have to use the superposition principle. And the superposition principle applies in many different arenas. And the superposition principle is simply that the total force acting on an object is the sum of all forces, or the superposition of all forces. Shouldn't be anything new if you're familiar with Newton's second law, F net equals ma. So we could, in a sense, also ask the question, if we keep our A the same and our B the same, and we introduce another object, C, and A was a positive charge, B was a negative charge, and let's give C a positive charge. And now we want to ask the question, what is the force experienced or acting on C? In a strictly qualitative way, C is going to feel an attraction from B, but it's also going to feel a push from A. So the question is, what is the net force going to be? And when you do these problems, it's important for you to use notation to indicate. So we want to say, what's the force on C due to B? So that's going to be K QC QB divided by the distance between them. And then we got to calculate the force on C due to A, and that is equal to K QC QA divided by the R between them. This was 0.20 meters, and let's say the distance between C and B is 0.10 meters. So it's important then to find the F net, and the F net is going to be the sum of the force felt by A plus the vector force felt from B. And I think I calculated the numbers for that. The force experienced on C due to A turns out to be, I won't show you the math because I think it's pretty straightforward, 2.6 newtons towards the right. And then the force experienced on C due to B turns out to be 1.4 newtons towards the left. So when we find the F net, of course, we can say due to A, it's going to be 2.6 newtons, and that's a positive number because it's headed to the right, plus negative 1.4. We're using negative only to indicate the direction, and then we end up with an answer that is 1.2 newtons towards the right. That's not how you spell right. There you go. So the F net acting on C is going to push this guy that way. And it will accelerate, of course. And you can see how important the R's are in this example. Okay, I hope that helps. Coulomb's law is pretty straightforward. It should look super familiar to you. The universal law of gravitation. It's the same format, which is kind of bizarre and interesting. We'll take a look at that a little bit. I've taken a look at some new way to express units and the units, the relationship between coulombs and amps and volts. Defined Coulomb's constant for you there. Understood that the K value is orders of magnitude greater than the gravitational constant. That means the electromagnetic force is massively stronger compared to the gravitational constant. Talked about the superposition principle, and that is when you want to find the total force acting on an object due to multiple nearby charges, you use the superposition principle, which is you find the superposition or sum of all the forces. And I've given you examples to look at that. There are some instances, or some things to remember, I should say, where Coulomb's law is limited. And this is what I'll leave you with today, the limitations of Coulomb's law. Highlight that so it looks nice. Okay, so first of all, Coulomb's law works when the charges Q1 and Q2 are small. When these charges get up to be huge, in reality, experimental evidence doesn't match as well to what Coulomb's law predicts. We also assume that the objects are spherical. And this is just to maintain a balanced spread or density of charges. As soon as you have an object that is not spherical, you have concentrations of charges on the sharp points, and we have to use calculus to take a look at what the flow or change of charges over an object. And the other limitation is that the objects are tiny or small compared to the distance between them. Coulomb's law is most accurately demonstrated in the lab when we describe the charges Q1 and Q2 as point charges. And that's when experimental evidence best matches what Coulomb's law predicts. And such things as electrons and protons. Okay, there you go. Hope that helps, and we will talk to you later.